liquid and solid fuel. That's what we discussed today. And then I will discuss the technology that used for solid and liquid fuel and what's their difference. And then I will talk about why we want this liquid fuel from this severe accident for loss of coolant accident. So then I will put a very simple introduction about what's a liquid fuel and their applications. Okay, I make this chart. So when we talk about the nuclear fuel cycle, actually including three components. One is the front-end process, the other is back-end process. In the center, that is our nuclear reactor. So the front-end process, the purpose is to make the fuel, to fabricate the fuel. And the back-end process, the purpose is how can we handle the fuel as a spent fuel after we put in the reactor. The center of the nuclear fuel cycle is a nuclear reactor. So the reactor is where we got the energy from, right? So that's the three major components of nuclear fuel cycle. In the front end, there are many processes. I summarize that into three processes here. You have mining and processing. And mining that you got the uranium from locations where you find the uranium, right? Then you do process, and then you have to enrich. Some reactors do not need to enrich, but most reactors will need to enrich the fuel from natural to the enrichment fuel, uranium. So enrichment here is actually enrichment process is a separation process. It separates the isotope uranium-235 from uranium-238. So you get one stream that have higher uranium-235. After that, you need to fabricate your fuel. So then you, after the fuel is fabricated, you put into the nuclear reactor, then you produce energy, right? In the back end, so you, in the back end first, after your fuel was burning in the nuclear reactor, and normally you need to store for a while. It's interim storage. If we do not want to reprocessing the fuel, after the fuel storage for a while and cool down, so you make them into the waste form, then dispose of it. So that will be just one through fuel cycle. So what we are doing now, most of the concept now is the one through fuel cycle. The things reprocessing will cost a lot of money and is not economically good. So they do one through fuel cycle. However, one through fuel cycle have many issues. The very long time half-life materials is in that waste. So it lasts thousands of years. So we need to reprocessing the fuel and get the useful materials and reburning again. So that we need reprocessing. So in this seminar, we will discuss about the reprocessing as well. So after you reprocess, you got uranium that go to the enrichment. You got plutonium that may not need enrichment and go to the fabrication directly. So then in the center of the nuclear reactor, so all the commercial reactor now, light water reactor in US, So in UK, they have a gas-cooled reactor as well. So thermal reactor and fast reactor, that's based on the neutron energy. So they split into thermal and fast. So what's the chemical change? So during you process your fuel, during your burning your fuel, so what's the chemical change? For example, this is a chemical change in the front end. So you have minerals, and you mining them, you make them into, milling them, make them into U3O8. U3O8 is a mixture of uranium oxide. and it's a yellow cake. It's look like yellow. Is very powder materials. So after that, we do a conversion process, and you make them into UF6. So UF6 can be a gas, can be a solid, and also can be a liquid based on the pressure at the room and at room temperature. So because UF6 can be a gas, that's why we use UF6 as an enriched agent here. So one thing I want to point out that enrichment is the isotope separation. So if fluorine have different isotopes in nature, so when you separate this isotope, you may separate the fluorine, not separate the uranium isotope, right? The good thing is that in nature, fluorine only have one isotope. So when we do enrichment, we only enrich uranium-235 in one stream. So that's one reason we use UF6. The other reason is because it's a gas, right? So we do the enrichment, and you got the enriched UF6. So after you do another chemical process, you can convert this enriched UF6 into nuclear fuel, different chemical form. For example, uranium dioxide and uranium metal mixed with zirconium as a metal fuel. So we use zirconium actually to stabilize uranium metal because uranium metal itself has a low melting temperature. So we put mainly the U-10-Zik uranium 10 zirconium. So then we do the fabrication, and we got a fuel rod, and we bronate. That's a solid fuel chemical change. So for the back end process, so there are currently they have two chemical process for reprocessing your fuel. One is they call it PRX. Actually, I call it wet process because they use water, H2O. So PRX and related aqueous process. So that's one process that is commercially available to process the spent fuel. And another process we call dry process that we do not need water. So we need molten salt or some other dry gas that you can also process your fuel. So we also call this dry process the pyrochemical process, and also related molten salt process. So the first process, PRX and aqueous process, they are commercially available, as I said. Unfortunately, pyrochemical process is not available, commercially available, but it has been done. It has been conducted research for many years, since the 1960s or 70s. We started the process, but unfortunately, so far we do not have a commercial facility that use this process to process the spent fuel. So I give the two figures here. One is the key components for PRX, that is centrifugal, and the other is a key component for the chemical process using molten salt, that's electric refiner. So from these two pictures, you may think, oh, these two facilities may be similar size. Unfortunately, they are very different size. So the first one, the PRX centrifugal is huge, and the electric refiner is very small. It's very compact. So if we want to use PRX, we need a huge plant. We need a huge land to build the reprocessing plant. However, if we use a pyrochemical process, you may not need that big land. You can just attach your processing facility to your reactor plant. So that means it's a very compact process. When we talk about this chemical processing, we need to think about the cost, right? So the self-guidability and the separation efficiency. So we will discuss about compare with these two processes to see what they are and what's the benefit and what's the advantage or disadvantage of this two process. So this is a table I made that for comparison these two processes. As we know that in the back end, we need cooling time. You need to cool down your spin field for some time. So for the pyrochemical process, we do not need a very long cooling time. But for PRX, you need longer cooling time. Why with that? Because PRX using water. Water its melting temperature is lower, is 100 degrees C. Its boiling temperature is lower, is 100 degrees C, and it's a moderator. When you have your spin field from your reactor, if you do not cool down for a while, there are still lots of neutron, delay neutron, and you also have a lot of fission materials there. So the moderator may slow down your neutron and make your system become critical. So then you have this critical issue that why for PRX you need a longer cooling time. Well, pyroprocessing does not need. It needs molten salt. Molten salt is radioactive stable, and molten salt clear is not a good moderator. So that's a good thing. And as I said, that for the pyrochemical, we use molten salt. For PRX, we use water. So water is good coolant, but for high temperature process, it's not coolant at all, right? So it's a liquid, and it's a liquid at room temperature. So any liquid waste is not good. So we can easily handle solid waste, but liquid waste is not easy. And for molten salt, it's a high radiation resistant and also easily to recycle. And at room temperature, it becomes solid and not liquid at all. For the proliferation concern, any nuclear equipment, we need to consider its proliferation things. So for the pyroprocessing, it's difficult to get the plutonium, pure plutonium. But if you want to get clear, you still can get, but it's difficult. But for the PRX, it's easy for you to get pure plutonium. So MICIS has a lower proliferation resistance. So the pyrochemical has a high proliferation resistance. Safety, as I said, it mainly is a criticality concern. So for pyrochemical process, we do not have that issue, and for the PRX, you have that issue. And as I said, the pyrochemical process is very small compared with PRX, so that means it can be high efficiency. It also operate at high temperature. For the waste, if you know the PRX process, most of the PRX process is waste is a nitric acid with fission product dissolved inside. That's high level waste. It's a lot. You process some fuel, you produce a lot of water solution with fission product dissolved. That high level waste. For the pyrochemical process, we do not have that issue. So everything is in the salt, and you can reprocess the salt and use the salt. And the location, as I just said, so you need a bigger land for PRX, but not big for the pyrochemical process. So that's all these comparisons show that the molten salt pyrochemical process is good than the PRX, right? Yes. So then you may ask me a question, why we do not use the pyrochemical process, right? So there's a lot of issues that we need to solve. So for PRX, it's the main issue is how to scale up it. We can make a kilogram how can we make 100 kilograms or something like this? That's an issue. For the Purex, we can easily scale up. We can make a huge plant and process and get all the fuel, spent fuel together and process in one location. So that's a big issue that we are still feeling about pyrochemical. So based on what I lectured now, so you can see that how many advantage we have for the molten salt, right? And we have a high radiation resistance for the molten salt. And if we use that process, so we have a short-cooled used fuel, you can process your spent fuel using molten salt related process. You have a high proliferation resistance. You do not have pure plutonium production. If you really want to get it, actually you still can get pure plutonium, but that will be very hard. So compare with the Purex. So you can handle a large quantity of fissile materials because we do not have that criticality issue. So no water moderator, we do not use water. So you can work at high temperature. You can make it very compact. You can make it on-site processing. On-site processing means you do not need to transport your spent fuel from your reactor plant to your processing plant. Transport the fuel actually costs money, costs a lot of money, right? So you can you may have a small amount of final waste and the solid waste after you process, and hopefully we have potential economical things. But no one has built this plant, so we currently don't know what economic benefit we can get. Okay, so that's the back end and the front end process. I just do a very simple introduction and show some knowledge about these two processes. For the reactor part, the center of the nuclear fuel cycle, we have a thermal reactor and a fast reactor electrode. I think the professor know all this. Maybe the student also know this, and we will very quickly pass this part. So we have water-cooled reactor that is a commercial reactor already operate for many, many years. And we have gas-cooled reactor that is also some gas-cooled reactor, helium-cooled reactor, they also build it. And there's one helium-cooled reactor that's in operation in China. So they have one test reactor, they have one that produces real electricity. And we have molten salt reactor concept. Molten salt reactor has been operated in 1960 to 1970, at the time frame around there, and at Oak Ridge National Lab in USA. However, we do not have any commercial molten salt reactor in operation or are planning to build now. So we have a fast reactor, the sodium-cooled fast reactor, and the lead-cooled fast reactor. And also we have a concept of molten salt molten salt fuel fast reactor. It's a molten salt chloride salt fast reactor. That is a concept of a company called Telepro. So they use chloride salt. So the Jinsuo reactor, you can see that I just want to show that the molten salt reactor here belong to the Jinsuo reactor concept in the temperature range about 600 to 900 degrees C. That is a molten salt fuel reactor. And they also have a very high temperature concept for the molten salt reactor. It calls molten salt cooled reactor. Personally, I do not call it molten salt cooled reactor as a molten salt reactor. It's a regular coolant. It's a regular coolant. For the molten salt reactor, traditionally the molten salt reactor is a molten salt fuel reactor. That means the molten salt is the coolant and the fuel. So that's I just want. But the company who is developing this molten salt cooled reactor, they also call their molten salt reactor. So it's molten salt is served as a regular coolant like liquid lead and sodium in the fast reactor. So for the field, the solid, for example, for the solid field, so what kind of field we have now available, we have studied. So we have U2, that is dioxide field. U2, uranium dioxide field can mix with plutonium dioxide field. They make the MOX field, is uranium plutonium oxide mixture. So oxide field has been used a lot, and it's commercial available. You can now the reactor plant can purchase and use them. And the other type of the field is a metal field. The metal field is they have a uranium zirconium metal. They have uranium zirconium uranium moly metal, UMO. They have uranium moly and plus some other additives metal and make a metal field. So a metal field has been used in the fast reactor. If you look back to the reactor they call as the experiment sodium-cooled reactor in Idaho National Lab, they use uranium zirconium field. And we also have a hydride field, uranium zirconium hydride. Here, the uranium actually is not in its hydride form. Zirconium is in its hydride form. Uranium is just dispersed in the zirconium hydride. And we also have some denser field, they call as uranium carbide and uranium nitride. So these two fields have been already fabricated, and they are much denser than uranium dioxide. So the fuel pellet, I showed that size. The fuel pellet is like this. You see that the picture showing that compared with this money, how big is that? So the fuel actually, after you got the fuel chemical form, you need to make fabrication. That is solid fuel. For molten salt fuel, you will see you do not need that. Normally, the fuel have a rod, and or you have a pebble, they call it transfer fuel. And anyway, so all these things is a complex fabrication process. For example, for this transfer fuel, the fuel sphere, actually called as pebble, is about 60 millimeter. Well, the fuel itself inside is very, very small. It's 0.5 millimeter. So then you can see that after you use this fuel, how much waste you have. You only have very small things that's useful, but you have a big things to hold it. So you got a lot of radioactive waste. So the transfer fuel, one of the big issues of transfer fuel is the waste. And for the fuel rod, we do not have that issue. The cladding is very thin, and however, you still need to fabricate it, and you also need to think about the corrosion of the cladding by the fuel as well as by the coolant. The fuel has an interaction with the cladding, and the coolant also have an interaction with the cladding. So normally we have to change the fuel rod, from the nuclear for some time. It's because it's one of the reasons is because of the corrosion of the cladding. Okay, so now we know the solid fuel, we know the reactor. So for operating reactor, for safely operating reactor, we need to keep our radioactive materials in the field. We do not want the radioactive materials to be released out. So we have, for the solid fuel, we have 5 barriers to keep your radioactive materials in your field. The first barrier is pellet. You have fuel pellet, and the fuel pellet have rotation of the fission product. Then you have the fuel cladding. That's a rod. That's a metal rod, metal cladding. Zirconium alloy or stainless steel. Anyway, it's very thin metal wall. So you keep that, in case you have the fuel cladding fill, and you have your primary coolant system, we hope that the fission product, everything released from the filled fuel, can be dissolved into the primary system and keep there. Coolant, including coolant and the system itself. If everything fails, so you still have your vessel. So this seems very safe. Unfortunately, if you have a very severe accident, such like what happened in Fukushima in Japan, so you do not have energy to supply your coolant. So you have a coolant, is a loss of coolant accident happen. So you do not have anything to cool down your fuel. So your fuel continually produce energy. Even there no fission reaction happen, you still have decay heat. You still need to cool down it. So if you do not have to cool down, then the accident will happen. So this picture is just after explosion of the Fukushima accident. So you release your radioactive materials out. So I want to point out this explosion is not because nuclear, it's because of hydrogen. So they produce hydrogen, then they have this core meltdown. Keep in mind for this solid fuel, we may have this severe accident got this core meltdown accident. Okay, for the liquid fuel, we talk about solid fuel, and then what the liquid fuel type will be. So there are two concepts of liquid fuel. There is one is liquid metal fuel. So they can use uranium bismuth and uranium iron as a fuel. They have low melting temperature. They can use it. This concept has a long time ago. So nobody is studying on this now, but they have this liquid metal fuel as well. Another liquid fuel is a molten salt fuel. They can be fluoride salt, as I said, used for thermal reactor, and you have chloride salt used for fast reactor. So I show that two pictures that is from our lab. The first picture, the white one, is like the table salt. It's sodium chloride. Clearly, this is not sodium chloride. It's lithium, sodium, and thorium fluoride. It's a very white color. It's very nice, actually, if you look very closely. And the second picture is beryllium, sodium, uranium salt fuel. That is green. So the green color is from the uranium tetrafluoride, is UF4. UF4 is green, and thorium THF4 is white. So it's a very good. All these two is purified salt. So we know that we know how, at least I lectured how to fabricate our solid fuel. How can we get the liquid fuel? So the liquid fuel main things for fluoride is UF4. UF4 is more stable than UF3 in your salt. So we can use three processes. For example, if you have enriched UF6, so you can use UF6 and reaction with the reductant. This can be a hydrogen, and then you reduce it to UF4. So chemically, this is theoretically is possible. And you can also, from the enriched or spent UO2. Spent UO2 is from the light water reactor, you have lots of spent UO2. So you can do uranium and dioxide reaction with HF, and then you produce UF4 together with the water release out. Another fluorination process is you can use some fluorides that can react with UO2, not HF. HF is very dangerous materials, so it's very toxic materials. So in our lab, we use zirconium fluoride. They are F4 can react with UO2 in the molten salt. Then we will produce UF4. And so at the same time, we produce zirconium oxide. So zirconium oxide is a solid. It's you can easily to separate a solid from a liquid, right? Mm-hmm. So you can filtrate it. So that's why I prefer that UF use zirconium fluoride that can be an easy way to get uranium dioxide into UF4. Another is you can use from enriched uranium metal that you can use any reductant to oxidant. You can use any oxidants that react with uranium and form UF4. So one oxidant is iron fluoride, FeF2. So FeF2 can react with uranium metal and to form UF4 in the molten salt. You have to put FeF2 in the molten salt, and then you put uranium metal. Uranium metal will dissolve, and the iron metal will be precipitated out. So then we know the field. We know how can we get the field. Then easier any core meltdown if we use liquid salt field or molten salt field. So actually, this accident is very difficult for liquid field. It may not happen. So first, the molten salt fuel is a coolant. The fuel actually is dissolving the coolant. When the coolant leak, so the fuel come out together with the coolant. It's not in the reactor core anymore. So you do not have any accident of this core meltdown because your fuel actually is liquid when you do it. And the fission materials, most of the fission materials can dissolve into the molten salt. That means when the salt is leaked from your system, it becomes solid. So the fission product was already in that solid. It won't release. I cannot see it completely not release anything, right? But most of them can be retained in the molten salt. And so as I said, the fuel materials and the fission materials, and they all will come out together with the coolant during loss of coolant accidents in this molten salt reactor. The salt have a high radiation capability of the fission product, and based on this, we do not have a core meltdown accidents in our liquid fuel. It's more safe. And other advantage, if you use liquid fuel or molten salt fuel, so you can operate high temperature. Where we want to operate high temperature, you can get high heat efficiency, and you can also use to produce some hydrogen, because electrolysis is hydrogen. Electrolysis is one way to produce hydrogen, but it needs high temperature. Low temperature have very low efficiency. And low pressure, so we know that the light water reactor has a high pressure when you operate the reactor, right? Mm-hmm. So, but for molten salt, we do not have that issue. So we do not have that things is we can operate at low pressure, and we can also use for cheaper and simple closed field cycle, and I will show that based on the parallel chemical process, right? So we can process the fuel directly, and you can also do online refueling and online reprocessing. But some people think online refueling and online reprocessing will lead some non-proliferation issue. But theoretically, you can do that, right? So easy fuel production and handling. We do not need that big wall of this transfer fuel. We do not need that cladding. We do not need to fuel rod. So it's easy production and also easy shutdown. So and also maintenance. So they also have a multiple application for molten salt reactor. You can make it small, you can make it large, and you can also make it very high temperature to apply to produce some other products. However, I lecture lots of advantage of modern salts. Everything have their two aspects, right? They also have their disadvantage because their complex chemistry is a very complex chemistry. You dissolve everything into the molten salt, and we do not have lessening experience. Even USA, the NRC does not have does not have much lessening experience to lessen a molten salt reactor, and so we may have a high radiation level in the primary system because you dissolve everything in your salt. Your salt is a coolant. So, so we need clearly more support from the government, more support from utility that we can make this molten salt reactor that become a reality. So we have this issue. Other issue, lack of lessening experience, more support from others. That is not really my lab doing. We are doing on the complex chemistry. So how can we move? How can we make our salt is more easy for us to handle and reduce their corrosion and degradation of the material in the salt? In our lab, we developed for a purification process. So the process is not originally developed by us, it's developed by the Oak Ridge National Lab in the 1960s to 70s. And but we integrate them together and make a system that we can purify the salt. So this including chemical, physical, and electrochemical separation. So for the salt, you got salt from some vendors and suppliers, you prepare them, you mix them. And the first thing you need to do is you vacuum your system and then filling with inert gas, vacuum and filling and vacuum and filling, or you heating your system to a certain temperature to get the moisture and other gas out. Do you have any gas in your salt? So when you vacuum it, that salt will be released out. And when you're heating it, your water will become moisture and you release it out. After that, we still have oxide in your salt. For example, you have salt oxide, you have uranium oxide. So what we do, if we use HF and H2 to purify your salt and make your salt reaction with HF, your oxide reaction with HF. We know that one process to get or UF4 is to reaction with UO2 with HF, right? So after you do this, you can convert most of the UO2 in your salt to be a UF4 and dissolve into the salt. So you remove the oxide, you remove metals, you remove metal fluoride. The H2 can remove the metal fluoride. And we use argon to purging again and to push all this dissolved HF and H2 in that. And then we do the physical separation of physical purification. So you got all these residual gases out. You got all your deposit that is solid, deposit oxide, and some fluoride that is not dissolved into your system out as well. If you still have some other metal fluoride in your salt, you can do electrochemical purification and to remove the metal fluoride in its metal form. Then finally you got the purified salt. We do this in our lab, and I think Adika, when they do the whole process to do the purification. After purify your salt, you can see very different interaction between the salt and your structured metal. So the BOSS 316H tested in the molten salt, in the same salt, uranium barium fluoride salt, we call it UNAC. So on the left, you can see that it's non-purified salt or thermal purified salt. You have a huge attack. several hundred micrometers attack. But on the right, you see that is all this chemical purified salt, and you only see very small amount of attack there. So that is just 1.24 micrometer. It's the same temperature, in the same condition. You can see that if you purify your salt, you can enhance you can reduce the corrosive of your salt, and very significantly. So it's from several hundred to less than 10 micrometer attack. This is the fluoride salt. Okay, so that is purification. Before you use the reactor, you purify your salt and you can reduce your corrosion. And we can also do online control, redox control that to reduce your corrosion as well. There are several ways that you can online control your redox potential to control your corrosion. So one is use gas, the HF and H2 cover gas. So if you control the ratio of HF and H2, you can control the redox potential of your salt. So then you can make your corrosion, you can reduce your corrosion by this. And the other method is that you use soluble redox couple. So this is including the uranium 4+ to uranium 3+. So you control the ratio. You can also control the redox potential. You can also reduce your corrosion as well. And the third method is you use reactive metal. For example, in the beryllium fluoride, lithium fluoride things, you use beryllium. And for the magnesium chloride, potassium chloride, and sodium chloride mixture, you can use magnesium. However, you have to select the metal whose potential is highest among the salt components. One thing I did not mention, you cannot use one pure salt. One pure salt always have a very high melting temperature. You need to use a salt mixture to reduce the melting temperature. So you may, they have some disadvantage if you use metal. They may forming some non-soluble deposits, such as oxide, that in your system that may result some other issue. You can also control mirror your redox potential by electrochemical method. One issue we are facing is that how can we get stable reference electrodes for this electrochemical monitoring? So this is just a draw to see if we want to get our molten salt reactor chemistry controlled, you need what system you need. So you need offer online salt purification system, and by control the chemistry, and by monitor the chemistry, and then you can control your chemistry of your molten salt reactor. However, as I said, we need to design this system. All the nuclear reactor, we need a chemistry control system, not only molten salt. Even the liquid lead reactor, lead is only one metal. It's very simple, but you still need to have a chemistry control system to control your coolant. Okay, so after we run our reactor, how can we handle the spent molten salt, right? So there are several processes that is all related with the molten salt system, and we already lectured this, the pyrochemical process. This including the electrochemical process. So you can separate your actinides from their in their metal form. So for this, you just use the salt, that's spent salt. You get the salt, and you can reprocess it directly. You do not need a chopping. You do not need to get all this, separate this cladding hull from your spent fuel, all things this. because our spin field is the molten salt. And this process is operated in molten salt. So that means it's simple to use electrochemical process to separate or purify your salt. So including the separate actinate, this can be easily and directly applied. So that's a very good thing that you can see that one lecture that the pyrochemical process very detailed. So because we have a very clear application in our molten salt treatment, spin field treatment. And another process you can use liquid pyrochemical extraction. So you can use bismuth lithium liquid contacting with the salt, and so then the actinate and the fission actinate can be extracted, and the fission product may also can be extracted to lithium metal. So then you handle the bismuth metal after the lithium dissolved into the salt and the actinate dissolved in the bismuth. So this process, you can also build a pyro contactor, like the centrifugal for the PRX. So for this process, they already experimented. We already done this. We can extract actinates from the salt, and this can also be used online. So you just contact your salt, your fuel salt, contact with bismuth and with lithium. So you can extract the fission and the actinate, and you have to put the actinate back to your salt as well, right? Another way is pyrofluorination. So this process is that after you finish your reactor, we have the spin field. So we want to get our uranium out, like what we do for the UO2. That's what we do for the uranium zirconium. What we can do, we use some fluorination process to make our uranium fluoride into UF6. We know that UF6 is a liquid, is a solid. Is a gas. So after you fluorination, you release your UF6 out. So you can do this fluorination. You can convert your actinate into gas, and for example, UF6, and so then you can got your fuel treatment or reprocessing. And draw some figure about showing that how this process is working. For example, if you have bismuth lithium, so you have rare earths, that fission products that go into the bismuth, and lithium will go into the salt. So then you extracted your fission product from your salt, and so your salt, you can reuse your salt in some other application. You can also do this electrolysis. For example, for chloride salt, you can produce chlorine gas at one electrode and produce the rare earth, deposit the rare earth in the other electrode, so you can separate your rare earth. And at the same time, clear, you can separate your actinates as well. So there are another process you can do in case that you think you make your bismuth to be second waste. So you can also use electrode to extract any materials that in your bismuth to deposit on electrode. So you can separate the fission product as well as actinates in solid from the molten salt. You can also separate your oxygen from your salt as well, to purify your salt. This is online purification. So I think this is my last slide for the introduction. I did not make any conclusion, but I think based on my lecture and the audience that can make a conclusion myself. So which one is easy, right? Okay, good. Thank you.
Excellent. Thank you, Prof. Zhang. Let's give applause to Prof. Thank you for the inspiring talk, Prof. Zhang. We learned from the solid fuel, liquid fuel, the advantages, the disadvantages. For example, we can avoid the core meltdown that was used to happen in the light water reactor, pressurized water reactor. By using the molten salt reactor, we could avoid somewhat the core meltdown, and it is safer. Yeah, of course, now the forum's open for the discussion. So I would like to ask the participant here to pose the question. Please, anyone? Maybe from Prof. Siddiq, because he's an expert in nuclear science and engineering. Maybe Prof. Siddiq, do you have any question about this topic to Professor Zhang? Please.
Student.
The student, the student. Yeah, the student of Prof. Siddiq. So you are now asked, requested to ask questions. So you can ask questions, please.
Because some students, they are simulating the fuel cycle, not related to uranium itself, but also uranium plutonium or thorium plutonium, as well as the minor iodine. I think chemically is different, especially for plutonium process. So what's your, general opinion if we want to? Because if you sorry, it's become.
Oh, no, it's yours.
Because if you load the fresh fuel, it's uranium, and this you have 4%. When you burn, you have burned up, and then coming into the south, fission product, plutonium.
Yes.
And
So yeah, most of the fission product has low potential than the uranium and the plutonium in molten salts. So if you separate them, the uranium and plutonium will first come out, deposit out. And then if you want continuous separation, you can get your fission product out.
And when you reprocess, just looking, and then coming in the plutonium process, it's become 4, plutonium 4, plutonium.
For you, for the fluoride salts, plutonium can be plutonium 3, PuF3, and uranium also can be UF3 as well. But fuel at the very beginning, we make it UF4. It's a little stable than UF3 in the salt. Yeah. If UF3, they can the UF3 can become to UF4 and uranium metal in the salt. So.
Yes, thank you. So I shifted the microphone to that side, please. Perhaps anybody would like to ask questions on the student side. You can ask question anything about the future of the.
We are recruiting students.
You're interested to go to USA.
Yeah.
You don't know the Virginia Tech campus is very beautiful.
Yeah.
I've been there in 2021 to visit Professor Zhang's laboratory. Very beautiful campus.
Normally we cover everything. We cover the tuition, we cover all your stipend. So you just go there to do research.
Yes.
Yeah. You do not need
Very nice
money.
Offer.
Yeah.
Yeah, please.
Good
Your
afternoon.
name first, and then your master student in which department?
My name is Efrin, and I'm from master student of chemistry department
Good.
of Bandung Institute of Technology. Thank you for the good presentation, sir. Mr. Jinsuo Zhang. I'm anxious to know about the use of nuclear energy. Is using the nuclear energy is the best answer to clean, friendly, and environmental energy? Since the accident of Chernobyl and Fukushima, also Pennsylvania, are the big disaster that ever happened? If you said yes, if you say yes, is there any research that proves you are right? And also, I have one question more. One question is about the limit of the heat that molten salt can tolerate or anticipate from LOCA. LOCA is lost of coolant accident.
Okay, so yeah, first, I believe that nuclear is a clean energy, and eventually it will be the only energy form. Actually, all the energy is from nuclear. All the energy in the Earth is from nuclear. So no matter what energy you use, for example, you use coal, you use solar, you use oil, all these things is from the sun, right? The sun is nuclear. Sun is nuclear. And the energy, the very basic form energy is nuclear energy. All the other energy is the second form. It is from there. So clearly that, and you're asking a nuclear professor, is nuclear is good, that's right? It's good, yeah, it's good. And so I think especially for here, Indonesia, you have a broad land distributed everywhere. You have a very remote island, and it's good to build some nuclear reactor, a small modular reactor in that island, and it can supply all the energy at the island, right? It's better for remote area, and for very population area, such like China, India, and maybe here as well, and they do not have much choice. Nuclear maybe is the best choice for them. So they need the land. They cannot use their land to build lots of other things. They need the land, and nuclear take a small land, and so that's I think, yeah. So the other question you said, LOCA, right? Loss of coolant accident. For this molten salt reactor, we do not have that issue. So for the water-cooled reactor, so you got your water out. It's completely released out to somewhere. But your core, your fuel is still in your core, in your reactor. Your fuel is still in your reactor. It's continue to produce heat. If you do not remove that heat, they will heat the cladding to be high temperature, then become melt. But for our case, if you have a coolant leak out, so the fuel come out with the coolant. It's not in the reactor core anymore. So reactor core, there are no fuel, and there's no fuel. So you do not have this core meltdown accidents that we always met in our electrode reactor. That the USR accident and the 3 island accident, they all from there. Yeah.
Thank you. So please, the next student, you can shift the microphone to the closest person who wants to ask question. Okay, it's okay. Okay, you can talk.
Okay. Thank you, Prof. And then Rino. Okay. I'm from physics department, and now I'm a postdoctoral student in Brin. And then about the corrosive, in the our conference, last conference, I heard about your topic about the corrosive materials. Yeah, and then now, when the salt is mixture with the fissile material, is there any impact in that graphite moderator? We use graphite moderator in molten salt.
Yes.
How about the corrosive impact with the graphite?
Yes. Thank you. The graphite moderator degradation is a big concern in our molten salt reactor. Is a huge concern actually. We do not want to change the graphite, but sometimes you have to, or sometimes because it's degradation, and the molten salt can intrusion into the graphite. And our experiments show that your graphite at 10 bar or 5 bar pressure, the salt can completely pass through graphite. Yeah, that's an issue.
That's the issue.
Yeah, that's an issue.
The big issue.
A big issue. Yeah.
Okay.
We do not want the pass back. We do not want the salts penetrating the graphite. But unfortunately, it's cannot make the graphite always have porosity.
Yeah.
You think we should change or like the replating or graphite? Like 4 years or
Change.
I don't know, I'm not a nuclear reactor design, but I know that they may have some, you have to change the graphite, right?
Yeah, we have to change theoretically.
Yeah, you have to change the graphite.
Or use some coating material.
Yeah, I can show
graphite.
I can show some picture about the graphite. Just a minute.
Good.
maybe I just follow the previous question while you're preparing the graphite. The following question actually, maybe it's not the issue of local, but when it's become boiling.
Boiling, okay, it's a very high temperature, boiling temperature.
First we simulate also the accident analysis when freezing, then boiling, the range. I mean, let's say 1,200 degrees C, it's become boiling.
No, it's at least 1,400 at least.
Okay.
It's very high.
So maybe the question is the range, the maximum. So we should keep control the temperature rising for the salt, not become the boil, or not become the freeze. Is that the question?
So,
if I'm not mistaken, the boiling point of the salt is around 1,200 degrees C, and then the operating of the reactor is about 700. So we have huge gap.
huge margin, yeah.
When accident happens.
It's possible.
The following question.
It's possible.
So how to control?
Yeah, it's possible. I don't know the exact design. I don't know how to control that. But if keep in mind the salt also has a positive volume change. You hit the salt volume start to increase, and the feedback will be negative. So it's not positive. So your fission, your chain reaction may stop. So you won't reach that temperature, then they stop. So this is some experiment from our test. This is graphite. This is the salt. You can see the salt can pass through the graphite. This is the pathway. And keep in mind, it's a 3D pathway, right? So this is 2D picture. So you can see that a lot of salt distribution. You cannot see the pathway, but you can image that inside there is a pathway to go to this surface area. So this is the thickness of the material we used. This is the thickness. So you can see it's from here to here, they just pass through. Yeah. Yeah, it's very significant. Yeah.
Without coating.
No, there are no coating. Graphite, there are no coating. We cannot use that coating. Graphite use a moderator.
Is that the labs?
Yeah.
Black bar.
The black bar?
Yeah.
This is just a molten material. Yeah. This is the SEM picture.
Is it high purity graphite?
This nuclear grade graphite. Yeah, we do a lot of tests on this. And
This program 100 hours.
it's 100 hours, 120 hours at 704. 704 is a thermal, is a second reactor operating temperature. So this is something we need to solve it.
Okay. So next, please. We still have time until 3:30. Still have question, please. Yeah, you can move the microphone. Yeah, of course.
For solid fuel.
We have people. We have people online. Have.
Yes, people online, mostly from the Torcon company. Yeah, if the online participant, if you want to ask question, please just turn on your microphone.
Can I ask first?
Yes, you can start.
Okay.
Your
Good.
name, please.
Yeah. Good afternoon, Professor Zhang. My name is Adi. I am an undergraduate under Mr. Siddiq's. Pak Siddiq. I want to ask about the molten salt purification. There is I saw that there is a lot of improvement on the purification, that the salt won't go through that hard on the graphite. Then how much does it improve the lifetime of the graphite? And I don't really think
The salt purification, we haven't do the test about the purification influence on the graphite intrusion. We mainly do the test is the salt purification on the corrosion of the metal. Yeah, so we haven't done that. So the picture what I show is a purified salt that's attacked on the graphite.
also it's not mixed with the fuel yet.
No, it's mixed with the
But
fuel.
mixed
The
with
fuel is already there. When I talk about the fuel salts, the uranium is already there. Yeah, it's uranium barium. We haven't do the test using a dirty salt with actinide without purification on graphite. What we do is already purified salt. So we don't know what the influence will be. Thank you. But I think there will be some influence.
Yeah, that's,
Yeah. Yeah,
yeah, it will be less severe on the graphite. Very interesting.
Good. So maybe anyone else you want to ask question? Maybe about the opportunity in Virginia Tech.
Yes, anybody want to know our university?
University, yeah. It's near.
How many PhD students?
So PhD student, maybe you can raise hands. 1,
2, 3.
4. 4 PhD students joining us. Oh, okay. 5. 5 PhD students in physics and in chemistry. And master student?
Yeah, everybody is master, I think.
Master student.
The rest of them.
Yeah. And undergrad student, we have undergrad student and postdoc researchers. So actually, Professor Zhang told us that he require a postdoctoral researcher.
Yeah, we're looking for we're looking for.
Yeah, he's looking for the postdoctoral fellow. If you are interested, you can apply to Professor Zhang. You can spend some time living in USA.
Yeah.
Virginia Tech is close to the capital, Washington, D.C.
Yeah.
Not very close.
1 hour flight is there? 1 hour flight. 1 hour flight.
It's Bandung to Jakarta.
Yeah. Yes.
There is a bus connecting between the campus and the airport.
Yeah.
But I guarantee you that the driving is very fast compared with here.
Yeah. There's no traffic.
There's no traffic.
No traffic.
Yeah, from our town to Washington DC.
Yeah.
If you drive in DC, then you have traffic.
Yeah. DC is very nice for students. Yeah, Prof.
DC.
The city is.
Oh, okay.
They said students enjoy living in the DC.
DC area.
Yeah.
It's very expensive. Very expensive.
Yeah.
So.
Yeah, please, Professor Siddiq would like to ask another question.
Wondering about sorry, you mentioned about the uranium and also the derivative. How about the thorium? When you keep in the thorium and also mix with
Thorium can also mix with. Yeah. Thorium has another. We do thorium. But we met the issue is that when we make the field, we want to know the composition of the field, right? What we do is use ICP-MS analysis. But the thorium fluoride does not dissolve into nitric acid. So we cannot know how much thorium in the salt after we fabricate. What we can only estimate is that use XPS. So that's one big things we made first. At the very beginning, zircon, the name with zircon, right? They have thorium there, but they do not have thorium now, right? They cannot get Helios, the high level enriched uranium for their thorium concepts.
But thorium name is quite fancy, fancier compared to uranium.
Thorium is like this. There are some countries like thorium, at least India and China. The reason is that they do not have much uranium. These two countries have not much uranium. So thorium itself is not the fissile materials. Thorium, you have to convert thorium into uranium. So one way to convert that, you still need some uranium 235 to start your reactor. And then you convert thorium into uranium 233. So uranium 233 is a fissile material. China and India, they like thorium-based reactor because they have this material. The Earth has more thorium than uranium.
No, right.
But we have also the thorium.
You have also
And the
Bangkai.
Bangka Island.
Oh, okay, good.
Monasit minerals.
But it's because the island, the mining of the tin and the derivative byproduct. But actually another island in Sulawesi, in the West Sulawesi, is not the byproduct, but mineral itself is thorium. So it's a byproduct and also the mineral in Indonesia. So that's why it's become sexy because here we have uranium of also very much also maybe 3 or 4 times thorium in Indonesia.
Okay,
So
good.
that's why they shift to.
Oh, you also.
But as you mentioned, we still need the uranium
Still need
for the reactor fuel.
The place is near Mamuju.
Yes, that's the
Near
Mamuju.
Mamuju. Yeah, near Mamuju.
Good.
We are doing also some research, mapping the. But it's a lot of job to do with the geology, geophysics or something. But we can, let's say, provide and then come to the lab and then this is some thorium extract something. But it's still a small amount.
Thorium oxide is very difficult to fabricate as well.
Very nice, very nice. Yeah, so I think it is time to end the seminar. So let's thank again Professor Zhang.
Thanks.
And I would like to say also thank you to the participant attending online. Pak Bob is attending online. Thank you, Pak Bob, Pak Delta, Bu Kirana, attending online. Thank you very much for your participation. So now the seminar end, and we will see you in the next FGD series LPPM ITB. So goodbye, bye-bye. Okay, so we can take a photo together in this room, Professor Zhang.
Okay, good.
Yeah, maybe this side is better because we have a lot of people.
Enggak, ke sana tuh ada tulisan.
Ya, boleh juga.
Atau di mana? Yang ada tulisan di situ.
Oh iya, new
Depan.
new
Lodge.
new launch.
Di lodge.